All right, well, happy Tuesday again. We are moving on. So hopefully containers went well. They're a lot of fun. We can do cool things with them. Just know that they're there, right? So another tool to add to our toolkit. So we're going to talk about recursion this week. Recursion is one of my favorite topics. A lot like classes, once you learn what recursion is, you might have the tendency to be like, I want to use this everywhere and everything, and I'm going to do inheritance everywhere, I'm going to do recursion everywhere, and it's not like that, right? Recursion will solve some kinds of problems for us very well, very easily, but it can't solve everything. So our general rule of thumb is anything that can be solved recursively with recursion, you can solve without it. You don't have to use it. It's just another shortcut, essentially. But not everything you can solve without recursion can be solved with recursion, right? It's not the universal tool. So it only works for some things here. So hopefully you had a chance to talk a little bit about recursion last semester. Maybe. No head nods? That's okay. So it's a function that calls itself. That's really all it is. Let's make sure I put that in the right folder here. So this is week 7. There we go. Week 7 recursion. So we can do some really simple recursion problems, recursion solutions, and then we can get into some more interesting ones. I really got to change this template. That one's obnoxious. All right. So first, really super easy recursive function here. We might just have a void one, and maybe we'll call this one countdown. Is that 2 words? That takes an int for number. So the idea with the recursive function is you need to know when to stop. We call that our base case. So the base case says, all right, you're done working, stop. If you're not done working, right, if you don't know what the solution is, we need to take that problem and make it approach the base case or a solution. How do I get closer to being done? How do I get closer to being solved and knowing what the answer is here? So for countdown, you can say, hey, if my number is less than or equal to 0, we'll see out blast off. That's my easy case. Right? I know what the solution is. If I'm 0 or less, we're done. If I'm not 0 or less, I'm going to see out the number, and then I'm going to call myself, countdown, given number minus 1. This is the recursive piece here. So it's not the semicolon. This is the recursive piece. Recursive. So if the function calls itself, that's recursion. So you can imagine if we give it 10, right? It says it's not 0 or less. Let's print out the number. Call it, it's 10 minus 1. That's 9. 9 is not 0 or less, right? So we get 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Don't even actually get 0, right? We just get blast off, right? But then it stops calling itself. So what's fun with these, yeah.
Wouldn't this still print the number at the end after blast off?
Oh, it would, you're right. Yeah, this probably should be in an else case. Thank you. And then it would keep recursing. Yeah, let's put that in an else block. That was totally on purpose. Yeah. All right, so let's try then to call countdown. Given 10. And if we put a breakpoint in and run it in debug mode, remember the debugger is your best friend. We love debug mode. We're going to see, okay, I'm at line 21, ready to go. So if I step into my code, to step into, now I'm at countdown, and number is 10. That's what you'd expect. So I'm going to keep going here. Countdown, I'm going to step in again, and notice, okay, I was at line 22, I was at line 17, now I'm at line 7. Number. I'm going to actually put the breakpoint in, kind of one right here. Put it right there. There we go. I'm going to step in. I'm going to continue to the next breakpoint. Step in, continue to the next breakpoint. Step in, continue. We're going to get a bunch of these, right? But as I click on them here, you can see the value of number. It's a little small over here. It's tracking. Every time you call the function, right, it has to know what the values of all the parameters are. It has to know what all those local values are in that function. So we've got all these functions on our call stack. Right? This is the stack of function calls. And when you call a new function, it goes on top. When that one's done, it comes off. So we can watch these ones go. So we're going to step into and continue and step into. Eventually, we'll get down to where number is small. There's number 3, number's 2, number's 1. All right, so now when we step in, now number is 0. So we've got all these calls on the call stack here. All right, at 0, we're going to print blast off. So we should have on our screen blast off. And then it should start unwinding, is what I like to call it. These calls will start coming off of the call stack. So we kind of wound all these up, added them all on, and then now they're going to start finishing here. So that one comes off, that one's done. Oh, I stepped too fast. Sorry, they all went away. If I would have done one line at a time. But there wasn't anything else to go to. It would have said, okay, now I'm down to my curly brace. There's no other work to do. They all come off the call stack. So that's simple recursion. Now, did we need recursion to count down from 10 to 0 and blast off? No, it's just a loop. So a lot of times, if the only thing you're doing with recursion is a loop, that one's really easy to do without recursion. You just put a loop in here. Right? How many of you folks are fond of math? Really? You have to do so much math in computer science. Okay, that's all right. Are you familiar with the Fibonacci sequence? That's a pretty common one here. So Fibonacci is really fun. So that one we're going to turn an int. So we'll say fib, because I don't remember how to spell Fibonacci. Is that okay? And we'll take an int for nth. Now Fibonacci, it's this really cool recursive definition. Right? It says, hey, if I'm the first or second number, I'm a 1. And I just know what it is. So I say, hey, if the nth is less than or equal to 2, I'm going to return a 1. This is I know how to solve this problem. Right? The first number is a 1, the second number is a 1. Every number after that is the sum of the 2 numbers before it. So the third number is 1 plus 1, so that's a 2. The fourth number is 1 plus 2, that's a 3. Right? The fifth number is 2 plus 3, it's 5. Right? So 1, 1, 2, 3, 5, 8, 13, 21, and it just keeps on going really interestingly like that. So this one I can solve. This is my base case here. Base case can solve. Okay? If it's not that, I'm going to return fib of nth minus 1 plus fib of nth minus 2. That's the mathematical definition, right? That's it. That's our recursive solution for Fibonacci. So if I want to get a certain fib number, or maybe we'll just count it for int, n is 0 or 1, right? N is less than or equal to, how about we go up to 40 maybe? N plus plus, because these start to get big pretty fast here. So we'll see out fib of n, or n, right? I think we called it, yeah, n. And an n line. So we give that a run. So we should get some numbers pretty quick. Oops, I didn't need the breakpoint here, sorry. Cool, 1, 1, 2, 3, 5, 8. That worked out pretty quick. So it might be nice if we had like, here's the value of n. So nth fib, I don't know, and then the number here. So let's go a little higher. Let's go maybe 50. It starts to slow down a little bit here. This is 267,433,000,701 million. Zoom it in a little bit. There we go. It's getting even slower now. 1.1 billion. $1.8 billion. Super exciting, right? I'm just waiting for the next one. What's going to happen with the next one? Remember when you go over your max int of like 2 some odd billion, 2 point something billion, you get garbage? We overflowed our max integer. That was sad. But C++ is happy to let you do it. Because why not? That's what you asked for. All right, so you notice it got kind of slow here. I'm just going to kill it for now. Let's just stop. Now, this was not a very efficient use of recursion. Really simple, really easy here. But remember what was happening when we did countdown? I said, okay, I remember I'm countdown here, and then I'm countdown of 9, I'm countdown of 8, countdown of 7, going on the call stack here. Well, when you get fib of 40 here, let me open up this and like draw a little picture, because drawing pictures is fun. I like drawing pictures. I really got to remember to bring my tablet. The draw mode's fun. So we wanted fib of 40. We said, okay, well that's easy. Well, that's fib of 39 plus fib of 38. Okay, well that one's easy. That's fib of 38 plus fib of 37. And this 38 says, okay, well I'm 37 plus 36. And this 38 says, okay, I'm 37 plus 36. And this 37 says, okay, I'm 36 plus 35. And this 36 says it, and this 36, and this 30. So do you see how this is like spiraling out of control really quick? Because what we literally have to do is add up the number 1 some billion number of times. That's the only number we ever get is a 1. So with fib of 40, we get 39, 39 gets 38, 38 gets 37, 36 going all the way down here. And it's, okay, now I get a 1, and then we go back to the second number, and it repeats. Eventually we'll get the 1, and then it goes back. And then it gets the third number, goes all the way down. So you get this like exponential amount of growth. I think this is even bigger than exponential. What's the factorial amount of growth here? Some ridiculous number of function calls to get from 40 to 2 billion, or 45, or whatever it was. Right? Numbers of 1. So this is not efficient here. This is bad fib. Right? This was not good. But it was super easy. Right? So a lot of times what we want to do to make this better is we need more information. Right? To do this recursively, we could do it much better if we had more information. Because counting all the way down to 1 is not good. Right? Isn't it much easier to count up? But we don't have all those other numbers here in those function calls. So I'm going to write an int for better fib here. That takes an int for nth. And again, the first base case, super easy. We can solve that one. If it's not that, we're going to do something else. Now, I'm going to have a helper fib. So I'm going to take an nth. I'm going to have an int for current nth. I'm going to have an int for current and an int for previous. So if you give me a lot more information here, I can start counting up instead of always counting down to 1. Right? So for my better fib here, I'm going to return my fib helper function. My nth is still the same. It's still the target nth. The current nth is going to be, right, I'm currently at 2, right? Because I know it is 1 or 1, but it's not there. So then you start counting up. The current is 1 and the previous is 1. Right? The nth, second number of Fibonacci, current was 1, previous was 1. Right? Because we had 1 and 1. Okay? Then for our fib helper function, our base case now is, did our current nth reach the nth? Right? Did we get to the nth we wanted? If we did, then we're done. Right? So we can say, hey, if my current nth is equal to the nth, I can return the current. I know that value. Right? If it's not that, anything other than that, now I could have an else here, but it's redundant because I have the return keyword here. We're going to return the fib helper function. Now we're going to recurse on ourselves. Nth is still the same. Current nth goes up by 1. Current, right, is going to be my current plus the previous, right? Because when nth goes up by 1, so when nth was 2, I had 1 and 1. When nth is 3, it's the sum of the previous 2, right? Current plus previous. And then my old previous, or the new previous, will be the old current. Right? So we pass 2, we get 1 and 1. So if we wanted the fifth fib number here, right, we'd expect, okay, nth is 5, so we'll call this function. When nth is 2, we had 1 and 1. Well, 2 is not 5, so let's add 1. So when nth is 3, the current value will be the sum of the previous 2. Now we'll get 2, previous was 1. And we call ourselves again. 3 is not 5. All right, so let's add. Let's go to 4. Well, 4 is going to be the sum of the previous 2. Right? And we keep on passing. So if we're giving more information, every step of the way here. I know here's what your new current is, here's what your previous was, so you can add those two up when you go, right? I can figure out if I can solve counting upward with our better fib. So now this one, you'll notice is going to be a whole lot faster here. Right? We didn't even see it. Again, it gets to be garbage after 47, but that's okay. You know what we could do instead of using integers if we wanted not garbage? What we'd have to use? You remember that in the back of your head? Longs. We never use those types, but you could. Right? If you want big integers. I don't know why it's not called big int. They're called longs. I guess they're just long integers. That makes sense, I guess. Right, we could use longs if we wanted. So we could make all of our values longs. Right, we'd have to change a bunch of them, right? Because our previous and our current. Probably not going to be a long nth, right? Because this was only 50. I don't think we're going to have over 2 billion nth of Fibonacci and figure out what that is here. Probably wouldn't go very well. We could try it, but if we wanted to change them all to longs, we could. So this uses essentially a private helper method. Nothing's marked as private here. You don't have to do anything like that here. But to ask for an nth number of Fibonacci, I don't want the user to have to give me all of this. Right? When we think of writing functions, writing a good abstract public interface, that API that people use, they shouldn't have to give you all the other stuff. Right? All they want to tell you is, hey, I want the nth Fibonacci number. If we need all that other stuff, we can do it ourselves. So we add a helper method that we're going to have here. So better fib itself is not recursive. There's nothing recursive here. The fib helper is the recursive function, because this is the one that's calling itself. Better fib doesn't do that, right? Because this is easier for someone to call. They don't have to tell me all that other information. And honestly, the more stuff users have to give you, the more likely they are to get it wrong, right? So the simpler we can make this, the more likely we are to get good information from our users. Now, I'm not going to say computer program users are dumb, but the average computer program user is a little bit dumb, right? So we got to make things simple for them. Okay, so that's our Fibonacci one here. Now, do we need to use recursion for this? No, it's just a loop, right? Right, so we could write an iterative solution. Iterative fib that takes an int for nth. And we get basically the same thing here. And then I'm just going to loop, right? So I'm going to have an int for current nth is 2. I'm just going to target this nth. I'm going to have an int for current is 1. An int for previous is 1. And then while my current nth does not equal the nth, start adding. Right, so I'll have an int maybe for next is current plus previous. Previous. I get the next value. Right, I'll take my current nth plus plus, and then my int for current will equal, oh, I'm sorry, previous first. Previous will equal the current. That's not an int here. We already know what current was. And then current will equal the next. Right, so we'll just keep on going. So calculate what the next one is, increase it here, move them back one. Eventually when I'm done, my nth should equal the current nth. Current nth should equal the nth, right? I can return the current. Right, it's just a loop here. So sometimes our recursion is just a loop. So which one of these do you think is more efficient to do in C++? Do you remember what we talked about when you call a recursive function, it has to stay on the call stack, and we have to track all those values? So every time we call fib helper, we're tracking 4 different arguments. So if I want fib of 45, I've got 45 times 4 integers stored in memory in that call stack somewhere. How many integers am I going to have to store with my iterative solution? Well, I got 1, 2, 3, 4, right? So the iterative solution is more efficient. And pretty much always going to be the case. Your iterative solutions will be more efficient. but sometimes the iterative solutions are hard, right? You okay with this one so far? Fib? Okay, let's do something more interesting. Let's think of our file system here. So if I open up my folder here, how would I write a program that counted how many files were in a given folder and all of its subfolders, and the subfolders, subfolders, and subfolders, 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 and subfolders, 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 and on and on and on. Can you imagine how we might do that?
Recursion.
With recursion, that's going to be the easy way, right? So add up all the files, and for every folder, repeat. Add up all the files, for every folder, repeat. Right? So recursion does this natural process here where it can just keep on going as far as it needs to go, because as far as I know, there's not a limit to the number of folders you can put inside of folders. At some point, the path gets to be too long and Windows gets upset. But it can have a pretty long path, right? So writing an iterative function for that gets to be rather tricky. Now, the interesting piece is you can write it iteratively, and you do it by using a stack. We haven't talked about those yet, but the call stack acts as that way of storing all that information for us, which is fun. So we'll come back to that later. So some solutions are harder to do iteratively. That's why we like recursion. So things like, hey, how many files do I have in this folder? It's kind of hard to solve without that. Another really classic one here is the Tower of Hanoi. This one's really fun. So there's a legend about these Towers of Hanoi here, which is, sure, if you find that interesting here. Let's get a solution here. So the idea is you have to move all of the disks from one peg to another peg. But the tricky part is here, you can't put a bigger disk on top of a smaller disk because it will get crushed or something like that here. So apparently there's some actual tower, and monks have to do this with a bunch of disks somewhere, but and when they actually finish it, the world will end or something like that, but because it takes a really long time to do. But so when we think about a base case, which is an easy solution, and something that's harder, that approaches the base case. This is really easy for this. So is it easy to move 7 disks? Do we know how to do that? No, we can't do that. But what if we moved 6 disks to a peg, and then moved the 7th disk to where we wanted it to go, and then put the 6 back on top of the 7? Would that be a little easier? Is that one step closer to a solution? Right? Because that would solve it, right? If I moved all 6 to here, and then the 7th one to here, and then all 6 back on top, that would solve it? Okay, well, let's try that. But now, can I move 6 disks? It's kind of hard to move 6. What if I moved 5 disks to here, moved the sixth disk here, and put the 5 back on top of 6? Can I do that? It's a little simpler, right? Oh, but moving 5 is kind of hard. What if I moved 4 and moved the 5th one and then put 4 on top of 5? Can I do that? A little simpler? All right, well, 4's hard. What about 3? Oh, well, 3's hard. What about 2? Well, 2's hard. How about 1? Can you move 1 disk? Moving 1 disk is super easy, right? That is the base case, moving 1 disk, right? And then, okay, I moved the 1. Now I'm mid-process of moving 2. So moving 2 was move the 2nd disk, put the 1 back on top. Right? Well, that was mid-process of moving 3. Okay, I moved 2, now move the 3rd disk, put those 2 back on top. Repeat the process for 2. Well, to move 2, I have to move 1, and then move 2, and then move 1 again. Right? Now I've moved 3, so let's move the 4th one. So the 4th one moves, and I have to repeat the process for 3. For 3 says, okay, well, I have to move 2. 2 says, okay, I have to move 1, and then 2, and then 1 again, and then move 3, and then move 2, which is to move 1, and then move 2, and then 1 again. You can kind of work your way down. So the solution's really fun when you show it here. I think, hang on, we need a 3x speed factor though. So there's moving 2, moving the 3rd disk, and repeats the process to move 2. And then we move the 4th disk, repeat the process to move 3, which is moving 2, and then moving the 3rd, and then moving 2 again. So each step gets a little longer, right? Because it has to wind up and unwind again. So now we're moving 3, which is moving 2. Right, so now we're moving the 5th one, which has to repeat, or no, that was 6. Now we have to repeat the moving 5, which moves 4. We had to move 3. Now we're putting the 3 back on top of the 4. Now we can move the 5th disk and repeat moving 4. So this one is really nice as a simple way to look at here. So here's Tower of Hanoi C++ solution. We're not even going to bother writing it ourselves here because it goes pretty quick. Code speedy. Right, here's this pseudocode algorithm for it, right? If it's more than 0, firstly, oh, I love that, firstly, move n-1 from A to B using C as storage, then move the disk we wanted to from A to C, and then move n-1 from B to C. Right? That's our goal here. That's how we would repeat this process. Okay? So in code, if you've got, I don't know, characters A, B, and C, sure, and the number we're moving, we're going to move number -1 instead of from A to C, right? We're going to move from A to B. And then move the disk we actually want here, the 7th disk or something, and then repeat the process, right? Flipped around here. That's the entire solution. Like, this is not very much code to do this recursively, right? So some number of disks from A, B is the storage, the temporary disk peg, and C is where we actually wanted it to go. Right? That was kind of fun. So, hey, if you want to move 3 disks, right? Disk 1 from A to C, 2 A to B, 1 C to B, 3 A to C. This is when we finally wanted to move here, right? So we had to move 2, which moves 1. Am I talking too much about this one? It's fun to watch. Right? So, Tower of Hanoi without recursion. Let's see, someone has a solution out here, I'm sure. Without recursion. Code review stack exchange. That looks like a lot of fun, right? This is, all right, they've got a loop, right? A while loop. They're moving disks in arrays, checking the case which route it has to go to, checking the number of disks. So here's a loop for the number of disks, and then going backwards. Wow, that looks like fun. So this is where recursion is an easier solution for us to write, because it takes care of all of that tracking for us, which is cool. So, and again, because there's probably not that many pegs, you're not going to have a crazy amount of recursion happening. Like in Fibonacci, it worked. We got to 2 billion. We had to add up 2 billion ones, but the most recursive calls we had on the stack was only like 45. Right? The most recursive calls we're going to have on our stack is 7. It's just going to do it a lot, right? Because 7 is 6, which is 5, which is 4, which is 3, which is 2, which is 1, and 3 is 2 and 1, right? 2, 1, 2, 1, and then 4 is 3, 2, 1, and 3 is 1, 2, 1, right? They just keep on going over and over and over again. So it's quick to do these. Should we paste those in for solutions with recursion, without recursion? Oh, that's without. Oh, it's just it was an add there. Right. Let's do this one here. Let's throw that one in. So here's our fib solution, and look, we're going to cite our source. Just drop in a little comment here. I got it from here. We're done, right? And I don't even want to do this one. This one's so gross, right? I'll leave the link here if you're curious. Or just iterative solution. It's ugly. All right. So this is probably more efficient. Right? It probably has to store less values. Maybe? I mean, this was not storing a lot of values. That might be tough to actually compare here, because you have to do a lot of other work behind the scenes here. That was our Fibonacci, and Towers of Hanoi solution. Now there's another really cool thing we can do with recursion that I'm fond of, is you can do this thing called backtracking. So if you have a maze, let's build a little maze here real quick. Let's come back to our main section here. So let's, before we do fib here, if we imagine we have a maze here, so let's do a char, or a vector of type char, call our maze. I gotta include vector. All right. There we go. So we got a maze. So let's go add all of our values here. Can I assign the values right in here? I'm trying to remember. That's fine. So we'll take our maze and we're going to push back a vector of char. I don't know, call that you need a row. Goodness. Why? I have no thoughts in my head here. C++. Create vector by values. Come on, Copilot. Initialize a vector. Is it a gimme code? Yeah, okay, yeah, I can use the curly braces. I was going crazy. I can do curly braces. So with a vector of vectors, right, we're going to have a vector inside of a vector. Curly brace, there we go. So we had maybe an S for start here, and then maybe an X for a wall, X for a wall, X for a wall, X for a wall, and then we'll repeat a couple rows here. See if we can't make this, get a maze we can solve. So if this one is open here, and maybe that one's open, let's make this whole row open here maybe. And then maybe we put a wall in there that you can't go through. And there's another wall, sure. Now we'll leave the wall here. And maybe we want to get to the end over here. So at some point we have to find an end to our maze here, right? What do you think? Does that look kind of like a maze? Imagine we put all those together. So people aren't too bad at mazes, right? We can kind of look at this and eyeball it and kind of trace it out with our mouse here. And I can find a solution here. There's also another solution if I want to go that direction, right? But I avoid this dead end, I avoid that dead end. Maybe we'll open that up to make it more dead endy, right? So solving this with a program can be a little tricky. So backtracking recursion says, let's try. I'm going to try a step and see if I found the solution, right? That's my base case. If I found the solution, I'm done. If I didn't find a solution, let's try and take another step. Did I reach the end? No, okay, take another step. Did I reach the end? No, take another step. Did I reach the end? No, take another step. That's it, right? Now, the backtracking recursion also is fun. It has a second base case, essentially. And the second base case is I can't take any more steps, right? We're at the end and we've solved the maze, we're done, or I can't take any more steps. There's no more recursion, there's no more work to do here. It's also a base case. Other than that, it's try and take a step. Let's go somewhere. So when we write our maze solver here, so our void maze solver, that takes a vector of char called the maze, right? And then it also needs to know the int row index and the int for the column index. Right? If you give me the maze to solve and tell me where I am, we can go solve this maze. Right? So the first thing was going to check, hey, did I find the solution? So, hey, if my maze at the row index dot at the column index is equal to end, then we're done. Right? See out, found a solution. Probably want a way to print this too, which would be nice. We can come back to that. We'll print it after. So if I found the solution, we're done. Right? Really, and we can probably just return, we're done. I guess everything else can go in an else, but sure. So this will stop our function. That way I don't need an else here. Found the solution. If I didn't find a solution, let's see, can I take another step? Right? Which way, so do you want to try going up first or down first or left first or right first? Which order should we go in? Up first, okay, and then what? Up, right, and then what? Down and left. Okay, so that'll be our algorithm. So we're going to try up, and we'll try right, we'll try down, we'll try left. Okay? So to go up, then, is our row going to change or our column going to change? Row's going to change. Okay, so if my row index -1 is greater than or equal to 0, I could probably, it's probably a fair location, right? Because I want to make sure I'm within bounds, right? Okay, so if it's within bounds, right? And now I can only move on spaces that are open, right? Or not walls, right? Don't step on the wall space. Probably pretty fair here, right? So if it's a valid index and then my maze dot at the row index -1 dot at the column index does not equal an x, right? Sorry, char here does not equal an x, or maybe if it is equal to a space, maybe that's probably pretty good, right? So if it's a space, so this is, can I go up, right? If I can go up, we're going to try. We're going to recurse. We're going to call a maze solver, give it the maze, give it row index -1, and give it column index. Let's recurse. Go up by 1. Right? That's our step for 1. Right? Then we said we're going to try right. So right here then is going to be my column index. Now go to the right means I'm increasing my column numbers, right? So that's +1. So I want to be less than my maze dot at the row index dot size. This seemed a little silly here, but no one ever told you mazes were square. So we can't just assume they're square, right? So make sure we're going off of the length of that row. Or, right, this is the number of columns in the row, is the length of the row. So get the vector of the row and count how many columns are in it, right? And then make sure that, okay, so the row index stays the same, and now column index +1 is a space, right? And then we'll recurse. We'll go column index +1, right? You feel okay so far? All right. Now, we have the same code, basically the same code twice. Are you feeling bad about it? You should. You should feel bad about it. We have the same code twice, right? So what if we had a little helper function that said, hey, can I go somewhere? Would that be nice? Save us a little bit of time here? I would save us a little. I'm glad you thought of that. We want to save some time here. So this will be a Boolean function then. You know, can go, given a maze and a row and a column. Can go to, how about can go to? Right? So first we're going to make sure that the row index and the column index are valid. This is the way I don't have to do it separately. I don't want a different one for row and a different one for column. We could, but that seems like a lot of work here. Right? So we can say, hey, if my row index is greater than or equal to 0 and the row index is less than maze.size, right? Between 0, including 0, and but less than the size, so it's a valid row index, right? And same with the column index. My column index is greater than or equal to 0, and the column index is less than my maze dot at the row index dot size. Column index. There we go. Right? Make sure those are valid. And my maze dot at the row index dot at the column index is equal to a space. if that's true, return true. Well, that's silly, right? You don't want to do that. We're just going to return that. Right? It's a little big, but that's okay. Right? Because if you say if something's true, return true, otherwise return false, you could just return the thing. Right? Save yourself some typing. Right? So can go to, make sure the row index is valid, the column index is valid, and that we're out of space here. And what's cool about that, remember way back when we talked about these AND operators being short-circuiting? This was probably like last fall. Good luck remembering anything that happened in the fall. Right? The first time it finds a false, C++ says, oh, well, if anything is false when I'm ANDing, the whole thing is false, I'm going to stop working. It's an efficiently lazy system, right? So if the row index is not greater than or equal to 0, if you tried to go up from row 0, I never look at these other things, because otherwise we'd have an invalid index here when I said, hey, is row of -1 a space? And it would crash. But it doesn't do that because it short circuits. It says, hey, as soon as one of these things is false, I don't even look at this. So I'm only ever going to get these indexes if they're valid indexes, which is fun. That's one of the benefits of these short circuit ANDs here. Okay? So now I can save a little bit of time here. So can I go then, right? For up is going to be can go to. Here's the maze, and then my row index -1 and the column index. Right? Isn't that a lot prettier? That was for up, right? And then this is going to be for can go right. Right? It's can go to. Missing a parenthesis there. There we go. Can go to, and now that was column, we said +1, right, to go to the right, and your row stays the same. Okay, and then how about down? Right, what changes with down? Not the column, right? What changes when we go down? The row, yeah, row +1. Okay, there's down, and then left. We don't go +1, we go -1 on our columns, right? Oh, that'll look really confusing. You could plus a -1. Perfectly legitimate code here. That's awful, don't do that, right? Okay, so can we go left? Okay, this is what we're going to try. So can we go somewhere? If we can't go any of those places, is it a dead end? Right? What we probably want to do here, because if we're imagining our algorithm here, we said we was going to go up and right, up and right, up and right, up and right first. So up, right, down, left. So from here, we're going to try up, we can't go up, right, we can't go right, down, we'd go down. Now we're here. The first thing we're going to try is up. Well, I can't go here because it's start here. All right, now can I go right? Yeah, let's go right. All right, can't go up, can I go right? Yeah, let's go right. Can't go up, can't go right, can I go down? Sure, let's go down. Can I go up? Well, from here, is the space above it open? It is. Well, we're going to get stuck in an infinite loop here pretty quick, right? So we need to pull a little Hansel and Gretel and leave some breadcrumbs. Because if you leave a breadcrumb, our algorithm says you can only step on a square if it's open. So if you put a breadcrumb down, you can't step on that square, right? So probably the first thing we want to do then, if we did not find a solution, is mark that we're on this space here, right? So mark the current space. So we'll take our maze dot at the row index dot at the column index and set it equal to, how about like a dot, the period mark? We could use anything here, but that's our little breadcrumb here. So we marked it, so I can't go to that space again. So now, as I'm moving around here, right, I can leave a breadcrumb, and leave a breadcrumb, leave a breadcrumb, leave a breadcrumb, right? And we're going to try up. Well, you can't go up, there's a breadcrumb there, let's go right. Okay, so go to the right, can't go up, go to the right, can't go into the right. We're going to try up, all right, go up, go up. We reached a dead end. Didn't get anywhere. So we can't go up, we can't go right, we can't go down, we can't go left. So this call will come off of the call stack. We'll come right back to here. Can't go anywhere, we'll come right back to here. Well, we tried up. Now it's going to try right. Can't go right. Now it's going to try down. Can I go down? Sure, let's go down. right? Puts a breadcrumb in here, we went down, we get to the end. Right, so leaving all these breadcrumbs will make it so we don't get stuck in infinite loops here. Right, and we also need a way to print the maze. So we probably want to be able to print it here, because that's pretty fun. So we'll just make a void print maze. Maze given the vector maze. So we can say for vector of char row in the maze, and then for char, I don't know, space in the row. We can see out the space. Now I don't want end lines, right? Because I want them all smushed together like until I get to the end of the row. And then I want an end line, right? Then I go to the next row, print out every character. Once that row's done, print the end line, right? Okay, so we should be able to print the maze. So when we solve it, maybe we say found a solution and call print maze, given the maze. Should we do that? Or maybe you want to print it every step of the way? How about that? We can do that, that's kind of fun. So how about before or after we mark it? How about after we mark it? So we'll mark our spot, then we'll print the maze and see what we get here. Okay, should we try it? Do you think it's gonna work? Semicolon there, right? So I want maze solver given the maze. Oh, and we have to tell it where to start, right? 0, 0. Now, we could go find the S mark and start. That's another, we can do that later. That's okay. We can figure something out like that. Let's see what we get here. Probably want a couple more new lines in between something here. So after all of that's done, do one more end line. There. I'll break it up a little bit better for us. All right. Let me zoom that in here. So our first step here, we stepped on the start. As we expected. We went down one, went to the right, went to the right, went down one, went to the right, went to the right, went up one, went up one. After this then, right, the next piece was going down one. Okay, we went down one. The next step was from here going down one. It didn't say we found a solution though. We went down one, went right one, nothing else to go, didn't find a solution, down, down, nothing else. No other steps to go. So something's not working right. Why aren't we finding a solution? Remember what our code did? We said, hey, if our position is the end here, can we go to the end space with our can go to code? Is this going to let us step on the end square if we're only looking for blanks? No, and that's another reason it's nice to have this function here. I don't have to fix it 4 different times. I can fix it one place here. So I can go there, right? Or if that's an end, I can go there, right? Space or an end, because the end is also a valid space, right? We want to go there. So adding a little or in here will help us check that. Now I should be able to find a solution. Right? Hey, we found a solution. And hey, we found a solution. Right? We reached the end here. Is that fun? Now, do you know why the maze is like all of a sudden getting changed here? What did we do? Why like we're losing those breadcrumb trails as we went up and down, like in those other dead ends? Do you remember what bad thing we did? Right? Maze solver is not taking a reference to a maze. So every time I pass it the maze, I'm passing a copy of the maze. Right? So when it marks the maze, it's marked its copy of the maze. And then it passes that marked copy, and passes that marked copy, and passes that marked copy. But when it hits one of those dead ends, that marked copy goes away, right? Because it had the previous marked copy. So if we pass this as a reference here, we should be able to keep all of our marks on there, our dead end marks. Right, so the first dead end was going up over this way, right? So we went up, and then all the way up here. Then we can see it was going down. right? We kept those other marks as we're passing the reference here, and we found our solution, right? So one other thing, if instead of printing every step, right, what if we only print it once we find a solution? Would that be a little bit nicer? Give us a little bit less printing here. So we'll just see here's a solution, and here's a solution, right? Is that a little bit nicer to see? We're not seeing every step of the way, but we can see which ones we did find.
I think the other one was better, where it didn't show you the messed up trail.
You don't like seeing where we've gone before? What if we wanted to like mark these as dead ends somehow? So we know it's not a trail, but we've shown that we've gone there. Or you like seeing only what is a valid path? Okay, instead of passing it. So if we pass it not by reference, we just get here's a path and here's a path for solutions. You like that better? Okay, that's fine. And we did overwrite the start space. That's a little sad, but that's okay. It's not the end of the world. What if we wanted to find out which of these solutions was a less, has the least amount of steps? Could we do that? Let's see which is the best possible solution we found to solve our maze here. Now this one's not super interesting, right? Maybe if we moved the end space, right, because they're the same number. But if we moved it here, we'd get two different solutions, and one has more steps than the other, right? This one definitely has less steps than this one, right? Going down and around. Can we do that? So to track that, we'd have to be tracking the number of steps it takes. This would probably be much nicer as a class then, because it has to be tracking other pieces of information, other sorts of things here. It doesn't have to be. Like there's ways we can do it, but then we'd have to be passing more values around, right? Like a step count every time. That could get a little tedious here. But we could do something like that. Don't have tons of time left. We could, I don't know if we'll get it done by 10:45. You want to wait for Thursday for that? All right, so we've got the project solution Thursday, and then we'll do the maze tracker that counts the number of steps, and then we'll talk about the next project. Leave those three things, right? Because we've got project 2 coming up, right? We've got spring break, templates, and then linked lists is lots of fun. So project 3 will be due probably about March 14th or so. So if you want to take all week off for your spring break, we'll still have 2 weeks to work on it, like usual. That was the goal. I would like you to not have to worry about stuff over break. Should we just, I can assign the project when you get back on the 5th. Would that be better? That we like not even tempted, because you'll be tempted to work on it, right? You're like, oh man, I really want to get this project done. I'm so excited to work on it over break. I know, I feel like that too. I'm so excited to get stuff done. All right, so let's plan for that. So we'll work on the rest of Recursion here. We'll go over the project solution. I'll give you the new one after we come back from break. Okay? Yeah, pretty cool. So we're cruising along. We are halfway through the semester now, right? Because we've had 6.5, 7 weeks or so. And the last week we've got work time. So we're officially halfway through. It's been great. If you got questions, let me know. Always happy to chat. I've got office hours. Esther runs the SI sessions. We've got drop-in tutoring in the Engineering Success Center. Is that what it is? Engineering Success Center? I forget. We've got so many letters. Yeah, so we got resources for you, but you got to tell somebody that you need help, right? We're probably not coming to you, right? You got to come to one of us. All right, if you got any questions, let me know. If not, I will see you folks for lab this afternoon.